So in this video, we're going to talk about uniform convergence. And before we get into any definitions, what I want to do is I want to get used to thinking about functions as sequences. So what I mean by this in the general setup is that you're going to have some sort of a function f sub n that's going to map whatever your favorite subset of the complex plane is to the complex plane. And maybe the function f sub n of z is going to look something like, I'm just making this up, but maybe something like e to the iz over n squared plus 1. And so the idea is that you want to understand what's going to happen to this function as n goes to infinity. Maybe we're only worried about values values z that are in some set g, where g is maybe the unit disk. So maybe it's some nice bounded, open, connected set, but whatever. So the domains for these functions are going to be the same. So as n increases, you'll get different functions, but all the domains and all the, so the set G remains the same. The what's called the codomain, so the kind of the values that you get out of the function all stay the same. So those are fixed. And then the only thing that's changing is our function. And as n increases, we want to understand what's going to happen. So depending on the set G, we might actually have different behavior depending on what the domain is. If you keep a bounded domain, then this numerator is going to be bounded, and then this whole thing will converge to 0 because you're going to have a bounded quantity over n squared plus 1 as the denominator goes to infinity. So by the squeeze theorem, we will get that this goes to 0. If G is the entire complex plane, well, then this e to the iz gets arbitrarily large. And so then you're going to have a tougher time evaluating what the limit is, or the limit might not even exist depending on what the set G is going to be. So anyway, so this is the idea of looking at functions as sequences. And then for each of these functions f sub n, you can just think of them as a normal function, right? So if you were to have f sub 5 of z, this is just the function e to the iz over 26. Okay, whatever, it's just e to the iz over a number. And as n increases, you get different functions, and you want to study what's the long-term behavior as n goes to infinity. So that's really the question: what happens as n goes to infinity? Okay, and so there's going to be two related types of convergence that we'll talk about here. And the first is just pointwise convergence. Okay, so there's pointwise convergence. So I'm going to just work with this in the abstract, and then we'll talk about specific examples soon. But first is pointwise convergence. And the idea with pointwise convergence is we're going to say that, so let's say we have a sequence f sub n. It's going to map some set G to the complex plane. Maybe we want G to be nice, maybe we don't. It probably doesn't matter too much at this point, but just an abstract sequence of functions f sub n. We're going to say that f sub n of z, so the limit of f sub n of z is equal to f of z pointwise if for each value z in the domain G, and for all values epsilon, there exists a value n so that for values n, little n, greater than or equal to big N, we have the usual definition of a limit: f sub n of z minus f of z is less than epsilon. Now, one thing that I have to emphasize with pointwise convergence basically says pick a point z, and then once you have a point z, now you're thinking, so pick z equals whatever, 2 or pi or whatever. So here, if we go back up to our example, let's just pick z equals pi. We have e to the I pi over n squared plus 1. So it's just some number over n squared plus 1. And once you pick this value, pi, then for that particular point, you can think of this as a sequence, and then you can just study this like normal sequences. There's really not too much different going on. And then if you were to pick a different point, instead of pi, if you were to pick 20, then you would have e to the 20i, and then you'd possibly get a different value of epsilon and n. Okay, and so your epsilons and your n's, namely your n's, are going to depend on whatever the point is that you're going to pick, possibly. So it's possible that your epsilon might depend on z itself. And if it does, that's called pointwise convergence. Okay, so here for each z, you can find, for each z and for all epsilon, you can find a capital N so that you get the usual statement of convergence, right? The outputs minus f of z is less than epsilon whenever little n's sufficiently large. Now, it has to, again, be emphasized here, capital N can, of course, we know it can depend on epsilon, but importantly, it can depend on z. Okay, and that's important because if you have a different value of z, maybe you have a different capital N. Okay, and that's pointwise convergence. So let's look at our first example of that. So let's look at the function. So let's consider f sub n mapping the complex plane to the complex plane, given by f sub n of z is z over n. So just something nice and simple. And here I'm going to let n be greater than or equal to 1. And what we want to do is we want to show that we have pointwise convergence, that the limit as n goes to infinity of z to the z over n is 0. Okay, so we want to show that here we have a pointwise convergence, that the sequence tends to 0. So let's fix a value z and let epsilon be given. I'm bothered by my capitalization here. So, and let epsilon be given. And then we want to do, just like all the usual limits, we want to do a little bit of work off to the side, and then we'll come back, we'll fill in the details, everything will be grand. So we want to show that there exists a capital N, so that if you have z over n minus 0, that's less than epsilon if little n is greater than or equal to capital N. And here, let's think about how this will work. The modulus of z over n minus 0 is, of course, the modulus of z. So just note, maybe I'll do this in a different color. So just note that, hopefully this isn't too annoying to look at, but just note that the modulus of z over n minus 0 is just the modulus of z over n. And that's going to be less than epsilon when little n is greater than the modulus of z over epsilon. So we can choose capital N to be, say, this quantity plus 1, or if you insist that capital N has to be an integer, you can just round up to the nearest integer. That's fine. Okay. And so, yeah, everything is fine. Here's our capital N. Notice that our capital N does, in fact, I want to write this just one way better here. It's just slightly hard to read because the pen stopped working. But capital N does depend on z. It's the modulus of z over epsilon plus 1. Okay, so capital N does depend on z. So whatever our z is, that'll change what our n is. And now we can just check, right, that if little n is greater than or equal to the modulus of z over epsilon plus 1, then the modulus of z over n minus 0 will be less than epsilon, and everything's fine. Okay, because you could, yeah, multiply both sides. Yeah, I'll let you fill in the details there, but everything works just fine. Okay, so that's pointwise convergence. So z over n converges pointwise to the 0 function if our domain is the complex numbers. Now, the last and second part of this video is uniform convergence. So uniform convergence is a slightly different statement than regular pointwise convergence, but it's going to have vastly different consequences. This is going to be really an exercise in understanding nested quantifiers. So what I mean by that is that if you've ever taken a proof course, you've invariably studied whether you take a for all there exists or there exists for all. You know, if you have reversed quantifiers, that can make a huge difference. If you've never taken a proof course, that's fine. I'll still explain the subtlety here. But the idea with uniform convergence is the following. So we're going to, again, start just like before. Let f sub n be a series of functions mapping some set g to the complex plane. We say that f sub n converges so we say that f sub n converges to f uniformly in G. And the way that I like to write this is that f sub n, so normal convergence you would write like this. So normal convergence, you would say f sub n converges to f. For uniform convergence, you would write it like this. So that's the one of the ways that it gets abbreviated. Some people like to write it as an arrow with a U. Some people like to write f sub n converges to f uniformly, so that it's kind of explicit what we're saying, but I'm going to use this double arrow notation, so that's going to mean uniform convergence. So we're going to say that this sequence of functions f sub n converges to f uniformly on G if for all epsilon there exists a capital N so that we have f sub n of z minus f of z is less than epsilon whenever n is greater than or equal to capital N, and that this holds for all values z in G. So here, notice that we put the for all z in G at the end. So what that does effectively is this is saying we get uniform convergence if for all epsilon we can find a capital N so that we get our normal inequality, and this normal inequality holds for all values of z at the same time with the same values of n. So here our n is not allowed to depend. So here n does not depend on z. Okay, it's important that we have a value of epsilon and capital N that works for all values z. That's what makes it uniform. It works uniformly for all values z. Okay, and so here I think a good example is again going to be this sequence of functions f sub n is z over n, but I'm going to change the domain to be over the unit disk. Okay, so again here our sequence f sub n of z is going to be z over n. And then it turns out that f sub n of z will converge to 0 uniformly. So uniformly on the open disk. Notice that changing the domain actually changed the behavior of the function. I didn't actually change what the function was itself. We just changed the domain, but that'll make a huge difference. And the reason for that is that if we let epsilon be given, and then we look at the same quantity, the modulus of z over n minus 0. This is again the modulus of z over n. But if z is on the unit disk, this is automatically less than 1 over n. And so that'll be less than epsilon when little n is greater than 1 over epsilon. And notice that, so we can choose capital N to be 1 over epsilon plus 1. And notice that this is now independent of z. So this is an estimate that's going to hold for all values z in the unit disk. Okay, so we use the fact that z was in the unit disk here, okay, with this inequality. But once we did that, now we have a value that's going to work for all values z. So our capital N no longer depends on z, and that's what makes it uniform. Okay, and then you can go back, fill in the algebra details in this. You have c over n minus 0 is less than epsilon, and everything's fine. Okay, so everything there is perfectly valid there. But that's uniform convergence versus pointwise convergence. Okay, so in the next video, we'll talk about what consequences we're going to have for uniform convergence. And then in later videos, we'll talk about uniform convergence of series, which is where we're headed in chapter 8 to talk about Taylor and Laurent series.